Hi everyone. In this video we will learn the new chapter called chemical kinetics. Kinetics mean the rate of chemical reaction. We've been learning about different kinds of chemical reactions, types of chemical reactions, the stoichiometric relationships of chemical reactions. So whenever a chemical reaction happens, there are a lot of questions. That what is happening inside it, what speed it is happening, is it slow, is it fast, is energy going in or out? So in the last chapter that you just did, that was energetics. We talked about the heat or energy changes that happen during a chemical reaction, like whether heat is absorbed or gained, bond dissociation energy, bond enthalpies. But in this unit, we will be talking about the speed at which reaction takes place. So the study of a rate of chemical reaction is called chemical kinetics. And with the definitions right here, the rate at which a chemical process occurs. And how do we calculate that rate? You know, we calculate it by there are different ways to calculate it. You know, you can figure it out by the change in the pH, you can figure it out by the change in the conductivity, or change in the mass or volume of the reactants or products, or change in the color of if you're dealing with transition metals or you're dealing with some colored compounds. And change in the color tells you that what speed reaction is happening. So anyway, no matter how you calculate it, uh, the the calculation is called kinetics. So we calculate the rate of reaction using the units. The units we use is moles per second. Okay, moles per time. You can say it moles cubic decimeter per second or moles cubic decimeter per minute. Okay, both of these could be the rate of reaction, or we can do it by the change in concentration divided by the change in time. That means delta C, the change in concentration divided by the change in time. And when we talk about change in concentration, we're talking about concentration of products as well as reactants. Okay, so let's move further on. First of all, how does a chemical reaction happen? We need to understand how does the reaction happen. To do that, we need to know the Culian model, the Culian theory. But before even going there, let's talk more about the rate of chemical reaction. So the rate of reaction, there are three kinds of rates of reaction. We can have the average rate of reaction, okay, average rate of reaction. We can have the initial rate of reaction, or we can have the instantaneous rate of reaction. So let's say I have a chemical reaction that is happening. So I have some reactants that are changing into the products, okay. So if I calculate this rate right here, this is the initial rate of reaction, okay. Right here is again, it's somewhere in the middle. Then here it is towards the end of the reaction, and if I take the average of this, that will be the average rate of reaction. So the initial rate of reaction decreases because if I'm converting a chemical A into a chemical B, these are my reactant, this is my reactant, this is my product. So as the reactant converts into the product, of course, the concentration of the reactant, let me explain the concentration right this. Whenever we put something in the parentheses, it represents concentration. So concentration of the product decreases, okay, and the concentration of the reactants, concentration of the reactants decreases and the concentration of the products increases. So the initial rate of reaction will decrease as the reaction moves on. Okay, so it's hard for me to just calculate, or it's not fair to just depend on the initial rate of reaction. So what the best way to do is to calculate the instantaneous rate of reaction. The instantaneous rate of reaction will be the rate of reaction at any point on the line. You know, we can calculate the instantaneous rate of reaction by drawing the tangent, okay, or to calculating the slope at any point. So if I want to calculate the slope at this point, then the difference between these two numbers will be my rate of reaction. So this is how we calculate it. And we use the formula again, delta C over delta T. Another example of the rate of reaction could be, you can understand it in terms of, like as I'm giving you the example of uh, rate is equal to change in concentration divided by change in time. And as I said, we calculated by concentration over, moles over seconds. Molarity over second, which is the molarity is the moles per cubic decimeter. Okay, moles per cubic decimeter, that's the molarity. So molarity over seconds. So moles per cubic decimeter per second. So this is the unit for my rate of reaction. Keep that in mind. So I'm going to take an example that my A is being converted into B. This is my reactant. This is my product. I'm going to assume that right now the time is 0. Okay, and the concentration of A is 1.00 molar. All right, this time is also 0 here. And the concentration of B is of course 0.0 molar because the reaction has not started yet. So now let's assume that the reaction starts. Okay, the time has passed to 2 seconds. So now the time is 2 seconds. Okay, this is my T1 and this is T2. And the concentration of A has gone down to 0.98 molar. Here, on the other hand, after 2 seconds, the concentration of B is 0.2 molar. Okay, 0.02 molar. Now, to calculate the change in the concentration of A and the change in concentration of B, I'm going to do the difference between the two. So let's first of all calculate the change in concentration of B. To calculate the rate of reaction of B, I will take the concentration, which is 0.02 minus 0.0. So concentration over time, that's my formula, the change in concentration over change in time. So this is my change in concentration. My concentration, this is C2 minus C1 kind of thing. That's not the formula, but this is how we do it. We always, uh, uh, you know, final number minus the initial value. And the time is going to be 2 minus 0. So when I do this math, I calculate 0.02 minus 0 over divided by 2 minus 0. My rate of reaction is going to be 0.01 molars per second. So this is my concentration of production of B, my products. So let's calculate the concentration of disappearance of A. So to calculate the concentration of disappearance of A, I started with 2. I started with 1 and I went down to 0.98. So 0.98 minus 1.0, that is the concentration because it went down. Okay, and the time went from 0 to 2 seconds. Okay, that is the difference. So this number is going to be a negative number. So I have negative 0.02, okay, over 2. Now the rate of reaction can never be negative because of course the reaction is happening. So we need a positive value for a rate of reaction. Uh, um, yes, it is disappearing. So since it's disappearing, that's another way to look at it, that it's disappearing. So I'm going to put a negative sign here because I want to make sure that my rate of reaction is a positive value. That is one thing. And two, why I say negative concentration of A, because the reactants are decreasing and products are increasing. So when I put this negative sign outside, it gives me positive value of 0.01 moles per second. So this is my concentration of A that is disappearing, which is equal to the concentration of B that is being formed. however you write it, moles per second or molarity per second, concentration per second. So this is how we calculate the rate of reaction. It has to be products minus reactants, and it has to be the value of the uh, second value before minus the initial value, and plus the both rates have to be equal, have to be the same. And also when we can calculate the concentration of the reactants, it is going to be negative number. So the reactant, the rate of reaction is negative delta A over delta T, okay, which is equal to concentration of B over delta T, all right? So this is how we calculate the rate of reaction. We can have different examples to do this, and that we could do even practice it in the class. Let's say you have another example. You have x-axis, and here is the y-axis. Whenever we calculate the slope, we always do y over x. So concentration of the y minus the concentration of the x. So I'm going to have a couple of values here to calculate my initial rate and the slope of the line. So let's assume that my x-axis is 0, 20, 40, 60, 80, and here I have 10, 20. So now to calculate the initial rate, this is my initial concentration. So this is x1, y1, okay? And then let's assume that I want to calculate it at x2. So my x2 right here, my x2 and y2. So let's look at the values of x2 and y2. The values for my x-axis is 20 and 50, and here it is 0 and 0. So now let's plug these numbers in into the same formula that we were doing before. That I will, to calculate the initial rate, I will do delta y over delta x, okay? Where y is the speed of the products, the velocity of the formation of the products, and this is the time. So basically this is the concentration and this is the time, okay? So y is y2 minus y1, which is 50 minus 0, and this is going to be 20 minus 0, okay, which is equal to 2.5 moles per cubic centimeter. It's given here, or moles per cubic centimeter. So this is how we calculate the initial rate. So bottom line is that to calculate the rate of the reaction, we are going to have concentration over time, and the unit is going to be moles per cubic decimeter per second. So now we need, the next thing we need to understand is the theory part of it, that how does actually the chemical reaction happen. The reaction will not happen unless the particles collide with each other. So the reactants, if I have substance A and substance B, the particles of substance A and B have to hit each other, and not only hit each other, but they have to hit each other with enough energy that they make a change, okay? They produce a product. It's, if they simply collide with each other and then go back, then nothing happens. It will still be a mixture. So molecules must collide with the correct orientation and with enough energy. So these are the conditions, okay, to cause the bond breakage and a new bond formation. So these are the conditions. These will be your questions that you need to understand. That molecules have to collide not only with enough energy, but also with proper orientation. No, that minimum energy that they need to collide and make a change is called activation energy. So I have explained this before in potential energy diagram, that we always add the energy. So energy is always added. Okay, so the minimum energy required to make that change happen is called activation energy, right here. Okay, it is the minimum amount of energy required for a reaction to occur. So you must understand this. We have learned about this in the energetics uh, unit as well. So here is another chart. Okay, this is the activation energy. So let's say I have a compound here. Here it is the compound of I have methanol here that has one bond with nitrogen, which has three bonds with carbon. So what's happening here is that I want to change the orientation of this compound. So I provide the energy to switch the orientation of these compounds, and you see that it starts working right here. You know, this thing that was aligned at 180 angle, it has changed to switch this, you know, the angle of it. So and you will see by the time the product comes, okay, now the C is attached, so the product is going to be the methanol bonds with C, which bonds with N. So this is the product, and this is your reactant. So we have to provide the initial energy to make that change, to start the change, and then the energy is released when that change happens. So this is my product right here. So the high point on the diagram is the transition state. Okay, the species present at the transition state is called activated complex. We cannot change the overall enthalpy of the reaction. That means the delta change will not, the delta H will not change. So this thing will not change. So no matter how how this reaction happens, the delta H, which is the energy of the products minus the heat of the reactants, will not change. Okay, so the enthalpy of will not change. But there are some factors that can affect that rate of reaction. So what can I do to speed up this reaction? Okay. First of all, I told you the Clayen theory. This is in your book, you know, the Clayen theory. You also need to read the page 165, which is the kinetic molecular theory of gases. And you also need to read the green part, which is on page 166, that is Clayen theory. But now I'm there where, what are the factors that affect this chemical reaction, the rates of reaction. So the rate of reaction can be affected by the physical state of reactants, by the concentration of the reactants, by the temperature, pressure of the catalyst, presence of a catalyst, and some other factors as well. Light can be a factor. There are some others too that I will mention as I move further on. So physical state of the reactants. So the more homogeneous the mixture is, the faster the reaction will work. Like what that means is that if I have solid, for example, let's say you take zinc solid and you put it into H2SO4, which is liquid, and you want to may produce a hydrogen gas. So you see there are different states of matter. So if they are all in same state of matter, like they're all gases, they will work faster. Or if they're all liquid, like in solution format, the reaction is the fastest. So keep that in mind. So the homogeneous mixture of the reactants makes the molecules react faster. The concentration of the reactants, if you increase the concentration, that increases the likelihood of the collision. So if we have too many molecules in this small area, common sense tells me that there is more probability of them to collide with each other. And more the collisions are, more the rate of reaction is, versus where we have enough space for them. So increasing the concentration increases the rate of reaction because it increases the number of collisions. Increases the temperature, increases not only the collision, the probability of more collisions, but also with greater energy. So you must understand temperature has a huge impact on rate of reaction, because as you increase the temperature, the kinetic energy increases. I also want you to, since I will use this time to mention that there is a average kinetic energy, okay, and there is a high kinetic energy. So there is a difference between the two. Like in container, if you have some gas particles, they all of them are not moving at the same speed. Like this molecule could be moving very fast, this molecule could be moving very slow, this could be moving, you know, kind of intermediate stage. So when we talk about, when we take the temperature here, the temperature gives me the average kinetic energy, but inside there some molecules could be moving faster than the other. So when we increase the temperature, that means we are increasing the average kinetic energy, that the overall, the more particles will be moving faster. Still, not every single particle will be moving faster. So keep that in mind as well. Anyway, so temperature makes a difference. As you increase the temperature, the kinetic energy increases, more play-ins, more with greater energy, so faster the rate the reaction will happen. Presence of a catalyst. So what does the catalyst do? The catalyst will speed up a chemical reaction by lowering the activation energy. Like for this particular reaction, or maybe I will make a clean picture. For this particular reaction, you need this much energy before the chemical reaction starts. Activated complex is right here. If this is 50 and this is 200, okay, you need the activation energy of 150 kilojoules. If you add the catalyst may start the chemical reaction much lower and give you the product faster. So with catalyst, the activation energy decreases and you can get the product faster. Okay, so the rate of activation energy with catalyst is this, and activation energy without catalyst is this. Okay, so keep, I'm sorry, you started from here, from the reactants, not from the bottom here. So, but what it doesn't change is it does not change delta H. Keep it in mind. The delta H remains same, no matter you add the catalyst or you don't add the catalyst. So the only thing catalyst does is it speeds up a chemical reaction. Another factor that I don't see here, or maybe I'll see in another slide, is the surface area. Okay, so let me explain here. Here it is telling you it is the hydrogen peroxide, the bromine and hydrogen. So catalyzed reaction happens this way, and uncatalyzed reactions happen this way. So catalyst decreases the activation energy of the reaction. So this is just another way of knowing this. One way catalyst can speed up the reaction is by holding the reactants together and helping bonds to break. So this is what it does. It does not take part in the chemical reaction. It doesn't become part of the reactants or the products. It only facilitates it. Okay, it only makes it happen faster. So the reaction rates, the concentration, if I increase the concentration, like I have the concentration, this is just telling you that how the concentration of A is decreasing. It's 1 molar here, and then it goes to 0.5, and then it goes to 0.3, and the B goes from 0 to 0.46 to 0.70. So as the concentration of A is decreasing, the concentration of B is increasing. So the rate of reaction can be determined by monitoring the change in concentration of either reactants or the products with the function of time. So you must understand it's delta C over delta T. But I did not mention one thing when we were talking about factors of chemical reaction, and that is the effect of surface area. Okay, that didn't mention here. The effect of surface area is that if I have Alka-Seltzer tablet, I have water here, and I put the whole Alka-Seltzer tablet in it. The water molecule will dissolve the outer layer of seltzer tablet, and then it gets in there. But on the other hand, if I grind the Alka-Seltzer tablet and I put in the powder here, the reaction will go faster. The whole thing will react all at once because I increased the surface area for this to happen. So increasing the surface area increases the rate of reaction. Okay, so all the factors that I gave you, all of them, if you increase them, whether it is the concentration, it's temperature, it's the catalyst, it is the surface area, whatever that is, it increases the rate of reaction. So these are they are part of your it's in your book. So I want you to read it very carefully and then understand it. I'm just thinking if there's anything else that I need to. Okay, that's about it. All right, so next thing we want to talk about is how to calculate the rate of reaction. So here is the rate of reaction, calculating the rate. Here is the time, and you see that as the time passes on, you have 50 seconds, and 100 seconds, and 150, and 200, and 300. The concentration of the products, concentration of the reactant is going down, Okay, so in this reaction, the concentration of butyl chloride was measured at various times. So you see the concentration is going down. It takes this much time to completely use all of it. Okay, and as the concentration goes down, you can calculate the rate of reaction. Okay, concentration over time. That's how you do it. It's a concentration over time. So you just take the concentration divided by the time. That gives you the average, the overall rate of the chemical reaction. Okay. Uh, the average rate decreases over time because eventually your reactants are decreasing. Okay, this number is increasing. So common sense tells you that if your denominator is increasing, the product is your final answer is going to go down. This is because as the reaction goes forward, there are fewer collisions between the reactant molecules. And plus because there is less concentration of the reactants. So a plot of butyl chloride versus time for this reaction yields a curve. So if I had the molarity here, as the rate goes down, as the time goes on, the concentration goes down. Okay, so here is the instantaneous reaction. This is exactly the same thing that I was just telling you before. Now, the slope of the line tangent to the curve at any point is called instantaneous rate. So as I was telling you that it's better to calculate the instantaneous rate to get the better feel of the rate of reaction. All reactions slow down over time. Therefore, the best indicator for the rate of a reaction is instantaneous rate near the beginning of the reaction. Okay, so this is the beginning of the reaction. So we can do these examples in class that how to collect or measure this rate of reaction. You will do the products minus reactants, and you also, when you have to calculate the rate of reaction, you go by the reactants that has the least coefficient. Okay, so as you see that 1 mole of calcium carbonate is producing 1 mole of calcium chloride. So if I have to calculate the rate of reaction, I would consider these components. On the graph, draw the effect of decreasing the temperature. So if you decrease the temperature, the reaction will slow down. Okay. If you add the catalyst, the the activation energy goes down. So we will do these examples in the class. Let's talk about Maxwell-Boltzmann distribution. Maxwell, there were two different people first of all, and they worked separately. It's just that they ended up with the same conclusion. That as you increase the temperature, the average kinetic energy increases. So if you look at this graph, what it tells you is that, let's assume this one here, that if this reaction is happening at 300 Kelvin, okay, this is how the reaction happens. Now, if I increase the temperature, I'm sorry, if I decrease the temperature, the average kinetic energy um, distributes. Okay, at any temperature there is a wide distribution of the kinetic energy. So since these are my reactants and these are my products, and this thing here, this area, gives me the average kinetic energy of the products, so average kinetic energy of the particles. So if I decrease the temperature, my curve goes up because I have to keep the area same. Okay, so if you decrease the temperature, the kinetic energy will spread around or distribute among the particles to keep the area same. If I increase the temperature, it will kind of spread. It will kind of bend down and you spread it more. So more you have it, the lower the curve will be. The less temperature you have it, because I need to keep the area same. So probability of finding the particles, the same energy, will increase. Okay, so this is Maxwell-Boltzmann. As the temperature increases, the curve flattens and broadens. At higher temperature, a large population of molecules have higher energy. So this is the probability that most of the particles have higher energy. Okay, that higher energy. This here, most of the particles, have less energy. So most of the particles have less energy, only this much, because the temperature is low. Here, most of the particles have higher energy. All right, so this is what it means. So as the temperature increases, so does the fraction of molecules that can overcome the activation energy. As a result, the reaction rate increases. Same thing with the catalyst. As you increase the catalyst, the reaction rate increases. So anyway, you need to keep in mind that the lower the temperature is, the higher the peak will go. The higher the temperature is, the flatter it will get. Okay, so that's about it. That's all this unit is about. It completes your whole chapter, and we will do the practice in the class. So if you don't get chance to listen to me tonight, we will do this lecture tomorrow in the class, and I will go from there. Well, thank you very much for your attention. I appreciate it. See you in class.